Hello everyone, my name is Samuel and I'm from the Electrical and Electronic Engineering Department of Imperial College London. And today I'll be presenting our paper where we use a passive acoustic transducer as a fluid flow sensor. So the objective of this experiment is to implement a passive structure that transduces the quantity of interest, which in our case is fluid flow, into an acoustic signal, and we then use an external microphone to receive the acoustic signal wirelessly. And this approach has several key advantages. The first one is the physical and electrical decoupling of sensor from electronics, which allow for reliable sealing of the monitored systems. The second thing is that this will allow for remote sensing applications where the passive structure may be in a more inaccessible or remote locations. Thirdly, the simplification of this approach also allows for the sensor to be used in harsher environments such as high temperature, toxic, or radiative environments. And finally, this approach also allows for integration of the passive transducer into the manufacturing process of the monitored system. So this slide here shows the operating concept of our passive transducer. The fluid flows through a cavity and drives a ball that's trapped inside the cavity in an oscillatory motion, as shown in the diagram on the right. The ball will then collide with the cavity wall as it oscillates, which will produce acoustic signals to be received by the microphone. And the faster the flow, the higher the ball cavity hit rate will be, which can be heard remotely. The pictures on the left show a 3D printed acoustic transducer, which consists of a square frustum-shaped cavity, a frame to mount the cavity and to be inserted to the pipe, a 5mm ball to be inserted into the cavity, as well as an outlet mesh to cover the whole transducer. And you can see that the transducer is not much larger than a 1 pound coin. And on the right, the sensor is fitted into the pipe of our calibrated lab flow rate and sealed with silicon sealant. And we use a simple analog contact microphone and mounted it on the pipe wall surface. And we use an oscilloscope to acquire the analog signal of the microphone when we pump water into the rig. And as you can see in the plot on the left, you can see acoustic pulses that were created by the ball cavity collision, and the microphone received those acoustic pulses. And the plot on the right shows the absolute values of the signals over a 5-second period for different flow rates. As expected, the higher the flow rate, the more peaks can be seen. And we can then find the mean of the signals and correlate them with the reference flow rate. So in this slide, the plot here shows the relationship between the signal mean and the water flow rate, and the correlation can be found. We also studied the reproducibility of the experiment by continuous data sampling for 5 minutes, and we segregate them to 65-second intervals. The mean of each intervals are then calculated and plotted as error bars as you can see in the plot. So to conclude, we could determine the relationship between the output of the passive transducer and the water flow rate. And repeatability was also demonstrated. We could also achieve remote sensing where the microphone was measuring the acoustic signal remotely from outside the pipe. And more future work can be done to improve the performance, such as optimizing the structural design of the transducer, as well as investigating and exploiting the acoustic waveform characteristics. And if you have more information, if you would like to have more information or collaboration, feel free to contact me with this email. And that concludes my presentation. Thank you for listening.